Welcome to the deep dive. Today, our mission is sharp and, well, critical, rapid yet incredibly thorough revision for the CompTIA Network plus certification exam.
hmm
We know that if you're gearing up for this test, time is precious. But, just flipping through flashcards, it probably won't cut it.
Not really, no.
You need that underlying why. So today, we're diving into the core expertise needed across all 5 major exam domains. We're talking networking fundamentals, implementations, operations, security, and troubleshooting. The goal is to give you that edge.
That's absolutely right. The Network Plus cert isn't just about memorizing acronyms or protocols. It really validates your ability to make critical, real-world design choices, troubleshooting decisions.
Exactly.
So this session, it's designed for high-impact knowledge reinforcement. We've pulled together 20 crucial exam-relevant scenarios, and we're not just handing you the answer. We're building the technical context around it, explaining why it's the answer.
Perfect. So think of this as a knowledge accelerator. We'll lay out the scenario, the options, give you a moment to think, lock in your answer,
Right.
and then we'll peel back the layers on the correct choice. We'll detail the principles, and maybe just as importantly, explain why the other options are technically wrong for that situation.
Okay.
Okay, let's unpack this. We'll jump straight into our first domain, foundational knowledge. All right, section 1, networking fundamentals. This covers the really basic stuff, but it's absolutely essential. Physical infrastructure, addressing schemes, core connectivity concepts.
The bedrock.
First question up, Q1 scenario. A network engineer is tasked with implementing a network that requires minimal latency and high throughput for the backbone. Which type of cable should they use? Options: A, Cat5e, B, Cat6a, single-mode fiber, D, multi-mode fiber.
Okay.
So think about those requirements. Minimal latency, high throughput, and importantly, the context is a network backbone. Take a second.
Yeah, that word backbone is really the major clue here, isn't it?
It absolutely is.
It implies, connecting core switches, maybe linking buildings, potentially over pretty long distances where you just can't afford performance drops.
Right. So considering that, the superior technical choice, the one that meets all those demands, is C, single-mode fiber.
Yeah, single-mode fiber, it's the undisputed champion for these high-performance backbones. And it's not just because it's fast. It really comes down to the physics. Single-mode fiber has this incredibly narrow core diameter, maybe 8 to 10 microns. That allows only a single path or mode for the light signal, usually from a precise laser, to travel down the fiber.
Okay, one path.
One path. And that drastically cuts down on signal dispersion. The light doesn't spread out as much. This means you get exceptional throughput and real minimal latency, even over tens of kilometers.
That makes sense. So why aren't the copper options like Cat5e or even Cat6a really viable here? I mean, Cat6a can handle 10 Gbps, right?
It can, yeah. Cat6a is fantastic. But it's bound by distance limits. You're typically looking at 100 meters maximum.
Right.
After that, things like electromagnetic interference, EMI, and just signal loss attenuation, they really start to hammer the performance. For a proper backbone, especially like in a campus setting, copper just doesn't have the reach or that sustained high performance you get with fiber.
Gotcha. And the difference between C and D, why not multi-mode fiber? It's still fiber.
Good question. Multimode fiber, option D, well, it has a larger core, often 50 or maybe 62.5 microns.
Okay, bigger core.
Bigger core, which lets multiple paths of light, multiple modes, travel at the same time. These are usually generated by cheaper light sources like LEDs or VCSELs.
Right.
Now, that makes it easier and cheaper for short runs, absolutely. But those multiple light paths, they cause something called modal dispersion. The light pulses essentially spread out and interfere with each other.
Okay.
And that severely limits its effective distance. You're often looking at less than, say, 550 meters at 10 GBPs, sometimes much less. So for those really long distance, high-speed backbone links, single mode is the only way to go.
Okay, that clarifies it beautifully. The architecture really dictates the medium. Let's move up the OSI stack a bit and talk layer 2 segmentation.
Sure.
Q2 scenario. A network technician needs to ensure that a specific host can communicate with another host on a different VLAN. What network device configuration is necessary to achieve this? Options: A, configure a static route on the switch. B, enable trunking on the switch ports. C, assign both hosts to the same VLAN. D, connects to the router for inter-VLAN routing.
Okay, classic VLAN scenario.
Yeah, imagine you've got, I don't know, a server in VLAN 10 and a desktop in VLAN 20. They're separated by that VLAN boundary. How do we let them talk?
Well, this really tests the core purpose of VLANs, right?
Yeah.
By design, A VLAN segments the network. It creates separate layer 2 broadcast domains. Traffic within the same VLAN, that gets switched. But traffic that needs to go between different VLANs, that has to be routed. It's a layer 3 function.
That necessity, that layer 3 requirement, points directly to the answer, doesn't it? It's got to be D, configure the router for inter-VLAN routing.
Precisely. Communication between separate broadcast domains needs layer 3 intelligence. That routing function, it's typically handled in one of two ways. Either by a physical router that's configured with sub-interfaces for each VLAN.
The old router on a stick.
Exactly, the classic router on a stick setup. Or, increasingly common these days, you'd use a layer 3 multi-layer switch, which can route and switch.
Now, I wonder, why isn't trunking option B the solution? Because you definitely need trunking enabled on the links between the switch and the router to carry multiple VLANs, right?
That's a really crucial distinction and a common point of confusion.
Yeah.
Yes, you absolutely need trunking. Trunking, usually using the 802.1q standard, is what allows that single physical link to carry traffic for lots of different VLANs by adding a tag to the Ethernet frame.
Okay.
So trunking is the enabling mechanism. It provides the pathway. But the actual action that allows communication forwarding the packet from one IP subnet associated with one VLAN to another IP subnet in a different VLAN, that action is routing. Without the router actually configured to route between those VLAN subnets, the tagged traffic goes across the trunk link, hits the router, and stops. It doesn't know where to go next. It can't be forwarded to the destination VLAN subnet.
So trunking carries it, routing directs it.
Perfectly put.
And obviously A and C are just non-starters, a static route on a standard layer 2 switch, useless for inter-VLAN, and putting both hosts in the same VLAN, well, that completely defeats the purpose of using VLANs for segmentation in the first place.
Right, it negates the whole setup.
Okay, that clears that up. Let's look at how addresses themselves are evolving. IPv4 and IPv6 coexistence.
The transition phase.
Q3 scenario. An organization is using both IPv4 and IPv6 addresses. Which of the following describes a dual stack implementation? Options. A. Running IPv4 and IPv6 simultaneously on the same network interfaces. B. Translating IPv4 addresses to IPv6 addresses. C. Tunneling IPv6 packets over an IPv4 network. D. Using NAT to convert between IPv4 and IPv6. We're in this period where, IPv4 is still everywhere, but IPv6 is becoming more and more necessary. How do we make them live together nicely on the same network?
The key conceptual difference to grasp between the transition methods is whether the protocols are running like side-by-side independently or if one is sort of hiding inside the other.
Okay, side-by-side versus hiding inside.
Yeah.
That definition, running them simultaneously, leads us straight to the correct answer here, which is A, running IPv4 and IPv6 simultaneously on the same network interfaces.
That's dual stack. Yep. It's generally considered the most straightforward and probably the most versatile IPv6 transition strategy. Every device, your laptop, your router, your server, it gets both an IPv4 address and an IPv6 address on its network interface.
Okay.
It can then talk natively with any other host, whether that host speaks IPv4 or IPv6. If the destination is IPv4 only, it uses its IPv4 address. If the destination speaks IPv6, it uses its IPv6 address. There's no complex conversion or wrapping needed.
Nice and clean. So how do options B and C, translation and tunneling, differ from that?
Yeah, they're totally different beasts. Translation option B involves methods like NAT64. That's where one address type is actually converted into the other. It's complex. It requires the translator device to keep track of state. It can be fragile. Tunneling, option C, is where you take an entire IPv6 packet and encapsulate it, like wrap it up completely inside an IPv4 header.
Okay.
This lets the IPv6 packet travel across parts of the network that only understand IPv4, but tunneling adds overhead. It adds complexity at the tunnel endpoints. Dual stack just avoids all that by letting the device speak both languages natively.
Got it. Native speakers versus translators or couriers.
Good analogy.
Excellent breakdown. Okay, finally for fundamentals, we have to face the music. The topic that probably causes the most anxiety for Network Plus candidates, subnetting.
Hi, yes. Subnetting. It's unavoidable.
Q4 scenario. A network administrator needs to calculate the network address for the IP address 192.168.17.77 with a subnet mask of 255.255.255.255.240. What is the network address options? A, 192.168.10.64, B, 192.168.10.65, C, 192.168.10.70, A, 192.168.168.10.72.
This is absolutely non-negotiable knowledge for the exam. You have the IP.77, you have the mask, .240 in the last octet. We need the starting point of the block that IP lives in.
Right. Let's break down the logic, nice and slow for everyone listening. The key, as you said, is that 255.255.255.240 mask. The first step is always to find the block size, or the magic number.
Okay.
You do that by taking 256, because there are 256 possible values in an octet, 0 through 255, and subtract the interesting octet value from the mask. So 256 minus 240.
256 minus 240, that gives us 16. So our blocks, our subnets, increment by 16 in that last octet.
Exactly right. So now you just list the starting points of the blocks. They are
Yeah.
0, 16, 32, 48, 64, 80, 96, and so on.
Right.
Now we look at our IP address, 192.168.10.77. We need to figure out which of those blocks contains 77.
Well, 77 is bigger than 64, but it's smaller than the next starting point, which is 80.
Perfect. So it falls into the block that starts at 64.
Which makes the correct network address A, 192.168.0.64. That's it. And just to round out the knowledge, because the exam might ask this too, that .240 mask is equivalent to a 28 prefix length, right? 24 network bits plus 4 more from the last octet.
Okay, 28.
So in this 28 subnet, the network address is 192.168.0.64. The broadcast address for this specific block would be the address right before the next network starts. The next network starts at .80, so the broadcast is 192.168.0.79.
Right. The last address in the block.
Exactly.
Yeah.
Which means the usable host addresses, the ones you can actually assign to devices, run from the one after the network address up to the one before the broadcast address.
Huh.
So 192.168.0.65, which is option B.
Oh, okay.
All the way up to 192.168.0.78. Knowing the network, broadcast, and usable range for common masks like 28 is crucial.
Okay, we've nailed down some fundamentals. Now let's move into section 2. Network implementations. This is where we focus on actually configuring services, setting up wireless, ensuring redundancy, putting the pieces together.
Making it work.
Q5. Scenario. You are configuring a DHCP server for a network. The network uses a subnet mask of 255.255.255.255.224. How many usable IP addresses are available for hosts in each subnet? Options: A8, B14, C30, D62.
Okay, another subnetting calculation, but a different angle this time.
Yep. This time it's purely about how many devices we can actually give addresses to using DHCP. The mask is .224.
Right. This tests the other half of the subnetting calculation rule.
Yeah.
First, you figure out the total number of addresses in the block, which is 2 raised to the power of the number of host bits. Then, critically, you apply the reserved address rule.
The infamous -2.
The infamous -2. You always lose 2.
Okay, so if we crunch the numbers for a .224 mask, the correct answer is C, 30 usable IP addresses.
Let's walk through that to be sure. A 255.255.255.224 mask. What prefix length is that? Well, 256 minus 224 gives us 32. That's our block size.
Okay, block size 32.
Right. And 32 is 2 to the power 5. So that means there are 5 bits left for the host portion in the last octet. The prefix length is therefore 32 total bits minus 5 host bits, which is 27.
Got it. 27 means 5 host bits.
Okay, so 2 to the power of 5 host bits gives us 32 total addresses in each subnet block, 031, 3263, etc. Now, we apply that fundamental IP networking rule. You must reserve 2 addresses in every subnet.
The network address itself and the broadcast address for that subnet.
Exactly. So 32 total addresses minus those 2 reserved addresses leaves us with 30 usable IP addresses that you can actually assign to hosts via DHCP or static configuration.
And missing that -2 step is a really common mistake, isn't it?
Oh, absolutely. People calculate to 32 and forget to subtract the 2. It's a classic exam trap.
Okay, good reinforcement. Next up, Q6. This is a very practical decision when setting up Wi-Fi.
Wireless choices, yeah.
Q6. Scenario. A company wants to implement a wireless network with the best balance of range and speed. Which wireless standard should they use? Options: A, 802.1 and B, 802.11G, C, 802.1 of G, C, 802.1 and N, D, 802.1 AC.
Best balance. That's the key phrase.
Exactly. We're looking for a compromise here. Not necessarily the absolute fastest speed possible, but good speed combined with good practical coverage, across a typical office or home.
Right. And when you're implementing wireless, you learn pretty quickly there's this trade-off. Generally, the faster the frequency band you use, like 5 gigahertz versus 2.4 gigahertz, the shorter the wavelength of the radio waves.
Okay.
And shorter wavelengths have a harder time penetrating walls and obstacles, and they don't travel quite as far. So the trick is finding a standard that maybe cleverly uses the best of both worlds.
Okay, so which standard historically hit that sweet spot, that balance point? That would be C, 802.11n.
Yeah, 802.11, or Wi-Fi 4 as it's now called. It was pretty revolutionary when it came out. It introduced MIMO, multiple output, using multiple antennas to boost throughput significantly.
Right.
But more importantly for this question about balance, 802.11n was the first major standard to effectively operate on both the 2.4 gigahertz and the 5 gigahertz frequency bands.
Dual band.
Dual band, exactly. The 2.4 gigahertz band gives you that excellent range and better wall penetration needed for broad coverage. The 5 gigahertz band provides higher speeds and tends to have less interference from things like microwaves or Bluetooth. So using both is why Pro really offered the best balance of range and speed at its peak.
So why wouldn't we choose 802.NMFXE then? Wi-Fi 5. It's
Yeah.
much faster than in, isn't it?
It is significantly faster, yes. 802.1axe leverages wider channels, more sophisticated MIMO,
Okay.
but it achieves most of those speed gains primarily by operating in the cleaner, wider 5 gigahertz band.
Okay.
While many EC devices do offer backward compatibility on 2.4 gigahertz for older clients, the standard's real performance benefits are concentrated in that higher frequency. And that higher frequency inherently means a bit less raw range and penetration compared to the combined approach of 802.101 and AXE band. So AXE leans more towards speed and more towards balance.
Makes sense. Okay, let's revisit segmentation, but apply it to wireless this time. Q7. Q7 scenario. An administrator needs to configure a wireless network to support multiple SI dies on a single access point. Which feature should be utilized? Options. A. WPA2. B. 802.1x. C. VLAN tagging. D. MIMO.
Okay, one physical box, multiple network names.
Yep. Imagine you've got one access point hanging from the ceiling, but you need to broadcast, say, a corporate network, a guest network, maybe an IoT network, each with its own SSID. How do you keep their traffic separate?
Right. You need to make sure that the traffic from someone on the guest network stays completely separate from the corporate network traffic right from the moment it hits the access point's radio all the way back to the core network. This means applying that logical segmentation concept we talked about with VLANs, but applying it at the wireless access layer and connecting it to the wired infrastructure.
Okay, so the mechanism that bridges wireless SSI to wired VLANs, that has to be CVLAN tagging.
That's the one. This is a really foundational implementation concept. The access point itself, the AP, is configured to broadcast multiple SSIDs. Let's say a user connects to the guest SID. The AP internally associates traffic from that SID with a specific VLAN ID, maybe VLAN 99.
Okay.
Then, when the AP sends that guest traffic out onto the wired network towards the switch, it uses an 802.1q trunk link. It adds that VLAN 99 tag to the Ethernet frames. This tag tells the switches down the line, hey, this traffic belongs to the guest VLAN. It ensures that even though all the wireless traffic is funneling through the same physical AP and the same physical cable, the core network knows exactly which logical network segment it belongs to and keeps it properly isolated.
So just to clarify, if we didn't use VLAN tagging on that link between the AP and the switch, what would happen?
Great question. If that link wasn't configured as an 802.1q trunk, the switch would just assume all traffic coming from the AP belonged to whatever VLAN was configured as the native or access VLAN on that switch port. All your carefully separated SSID's guest, corporate IoT, would effectively merge into one single broadcast domain as soon as they hit the wired network. The segmentation would be completely lost. VLAN tagging is absolutely the glue here.
Got it. Okay, here's where Layer 3 implementation gets, as I said, really interesting. Q8 is about maximizing hardware utility and uptime.
Redundancy protocols, always important.
Q8 scenario. During a network implementation, you need to ensure redundancy and load balancing at Layer 3. Which protocol would you use? Options. A. HSRP, B. VRRP, C. GLBP, D. RIP.
Okay, redundancy and load balancing, two requirements.
Yeah, we're not just looking for a passive backup gateway that sits idle until the main one fails. We want two or more gateways to be actively sharing the traffic load coming from the clients.
Right. This question tests whether you know the specific differences between the common first-hop redundancy protocols, or FHRPs. Most people think redundancy and immediately jump to HSRP or VRP, but that load balancing requirement is the crucial filter here.
It certainly narrows it down. The only protocol listed there that uniquely offers both redundancy and active load balancing is CGLBP, the Gateway Load Balancing Protocol.
Correct. This is a critical insight for Network Plus boots.
Okay.
Both HSRP, which is Cisco proprietary, and VRRP, which is an open standard. They are primarily designed around an active standby model.
Okay.
They work by having a group of routers share a single virtual IP address and, importantly, a single virtual MAC key address. One router is elected active and handles all the traffic destined for the virtual IP. If the active router fails, one of the standby routers takes over the virtual IP and MA address.
but only one is working at a time.
Exactly. Only one router is actively forwarding traffic at any given moment. The standby routers are just standing by.
So how does GLBP manage to do the actual load balancing that HSRP and VRRP can't?
GLBP, which is also Cisco proprietary, operates quite differently under the hood. While it also uses a single virtual IP address for the clients to use as their default gateway, it employs multiple virtual MA addresses.
Okay, multiple MAs.
Multiple virtual MCs. One router in the GLBP group is elected the Active Virtual Gateway, or AVG. The AVG is responsible for answering ARP requests for the shared virtual IP address.
Right.
But here's the clever part. The AVG doesn't just give out its own MSC address in the ARP reply. It intelligently distributes the replies, assigning different client machines on the subnet to use the virtual MAC addresses of different routers within the GLBP group. These other routers are called Active Virtual Forwarders, or AVFs.
So different clients get pointed to different physical routers, even though they all use the same gateway IP.
Precisely. This means all the participating routers in the GLBP group can be actively forwarding traffic simultaneously, each handling traffic for the clients that were assigned its specific virtual MAC address. You get true Layer 3 load balancing across your gateways, along with the redundancy if one fails. It really maximizes your hardware investment and throughput.
That's a much smarter system. Very cool. All right, shifting gears now into a really critical domain. Section 3, Network Security. This is all about spotting threats, locking down access with authentication, and using smart segmentation to protect the network perimeter.
Defense in depth.
Let's start with detecting a common Layer 2 attack. Q9 scenario. A network administrator notices unusual traffic patterns and suspects a possible ARP spoofing attack. Which tool would be most effective in detecting and confirming this type of attack? Options. A. Wireshark, B. Nmap, C. Netstat, D. Tracered.
ARP spoofing. Messing with MAC to IP mappings.
Yeah, it's nasty. An attacker basically shouts, hey everyone, the gateway's IP address, that now belongs to my MC address, so they can intercept traffic. How do you actually see that happening down at the packet level?
Well, since ARP itself is a Layer 2 protocol, operating just above the physical layer, you need a tool that can capture and dissect the raw network frames. You need deep packet inspection capabilities to spot those telltale anomalies in the MC to IP relationships.
Okay, deep packet inspection points pretty clearly to the winner here. A. Wireshark.
Absolutely. Wireshark is just indispensable for this kind of analysis. It grabs the raw packets flying across the network interface and lets you filter and examine them in incredibly fine detail.
So what exactly would you look for in Wireshark to confirm ARP spoofing?
You'd set up a capture filter, specifically for ARP packets. Then you'd watch for things like 1. A flood of unsolicited ARP replies. Legitimate devices don't usually spam ARP replies constantly. 2. You'd look for replies where the same IP address, like the default gateway's IP, is suddenly being claimed by a mass address that's different from the legitimate gateway's MC.
Oh, the conflict.
Exactly. Or you might see your own IP address being claimed by someone else's MA. Those conflicting or rapidly changing ME address mappings for key IP addresses are the dead giveaway that ARP spoofing is happening.
Right, so why wouldn't something like Nmap or Netstat work here? They're network tools.
They are, but they serve different purposes. Nmap, option B, is a network mapper and scanner. It's great for finding live hosts and checking which ports are open on remote systems by sending probes. It doesn't analyze the low-level ARP traffic itself.
Okay.
And Netstat, option C, primarily shows you information about your own local machine's network connections, which ports your machine has open, active TCP UDP sessions, the local routing table. Again, it's not looking at the ARP protocol messages being exchanged on the wire. Tracered, D, just shows the path packets take. Only Wireshark gives you that deep protocol view.
Got it. Okay, let's move to locking down wireless access properly. Q10.
Wireless security, always key.
Q10. Scenario. A company is setting up a wireless network and wants to ensure that only authorized devices can connect. Which security protocol should they implement to achieve this? Options. A. WIBP, BWP2 with pre-shared key, C. WPA2 with 802.1x authentication, D. Open network with MS Seltzer filtering.
Okay, authorized devices. Sounds like they need something robust.
Yeah, we're talking enterprise-grade security here. We need a system that really guarantees authorization for every single user or device individually, not just relying on a password that everyone shares.
Right, and that difference between a shared secret, like a pre-shared key, and individual credentials becomes hugely important in larger environments, especially where you need accountability and need to easily revoke access for specific users.
So the strongest, most manageable, and most secure option listed here is CWPA2 with 802.1x 2.1x authentication.
Definitely. Implementing WPA2 encryption combined with 802.1x authentication is the gold standard for enterprise wireless security. It works by integrating with a central authentication, authorization, and accounting server, usually using the radius protocol.
AAA server, okay.
Yeah. So unlike the pre-shared key model, option B, where everybody types in the same Wi-Fi password with 802.1x, each user or device has to authenticate using unique credentials, like a username and password, or maybe a digital certificate, before the network even allows them to connect and get an IP address.
Much more granular control.
Massively. Think about it. If an employee leaves the company with 802.1x, you just disable their individual account in the central directory, like Active Directory, boom, their access is instantly revoked.
Right.
With a pre-shared key, you'd have to change the password on all the access points and then communicate the new password to every single legitimate user. It's a huge operational headache and security risk while you're doing it.
Makes sense. Now, what about option D, open network with MC filtering? That sounds like it tries to authorize devices based on their MAC address. Why is that considered weak?
MC filtering. It's often called security through obscurity, which is not really security at all.
Yeah, okay.
While it seems like a good idea only allowing devices with specific hardware MC addresses to connect to where, the problem is that MC addresses operate at layer 2 and are incredibly easy to spoof or change in software. Oh yeah, an attacker can easily sniff the wireless traffic, find the MC address of a device that is authorized, and then just reconfigure their own wireless card to use that captured MC address. Within minutes, they can bypass the filter completely. It provides almost zero meaningful protection against anyone even slightly determined. WEPA is ancient and completely broken, by the way. Don't even consider it.
Good to know. MAC filtering is basically a flimsy screen door.
Pretty much.
Right. Q11 looks at dealing with large-scale external attacks. The dreaded DDoS.
Distributed denial of service. Flooding the gates.
Q11 scenario. An organization is experiencing a DDoS attack. Which of the following techniques can help mitigate the impact of the attack? Options. A, implementing MSC filtering on all network devices. B, configuring rate limiting on the network firewall. C, disabling unused network services. D, enabling port mirroring on the switches. The core problem here is just the sheer volume, right? Millions, maybe billions of connection requests or packets flooding the network from potentially thousands of compromised machines all over the internet. We need a way to somehow throttle that flood at the entry point.
Exactly. The mitigation has to deal with that overwhelming volume of traffic, which often looks legitimate individually but is malicious in aggregate. And it needs to happen right at the network boundary, typically at the firewall or border router.
Okay, so which of these techniques directly tackles that volume issue? The most effective immediate mitigation listed is B, configuring rate limiting on the network firewall.
That's the primary tool for this specific problem. Rate limiting is a crucial firewall or router feature that lets you control and restrict the maximum amount of incoming traffic or the number of connections allowed to a specific network resource within a given time frame.
Like a speed bump for traffic.
Sort of, yeah.
Yeah.
It acts like a digital dam. It prevents your network infrastructure, your firewall CPU, your server's resources, your bandwidth, from being completely swamped by the excessive requests that define a DDoS attack.
Okay.
So you might configure to say, only allow, say, 10,000 new connections per second to the web server. Even if the attack is sending 1 million requests per second, the rate limit ensures the server only has to deal with a manageable amount, keeping it operational, even if some legitimate users might experience a temporary delay.
Right. Now, options A and C, MC filtering and disabling unused services, seem like generally good security practices. Why don't they stop a DDoS?
Good point.
Yeah.
Disabling unused services, option C, is excellent security hygiene. It reduces your attack surface. But a DDoS attack usually targets services that you need to keep running, like your main website, HTTPS, or your DNS servers. So disabling them isn't an option.
Yeah.
And MC filtering, option A, as we just discussed, operates at layer 2 and is about controlling local network access. A DDoS attack is coming from external IP addresses over the internet, layer 3. MSC filtering is completely irrelevant to stopping that kind of flood. Port mirroring D is for monitoring, not mitigation. You need something that tackles the volumetric flood.
Got it. Rate limiting hits the volume problem directly. Finally, for security, Q12 addresses a fundamental security flaw that sadly still crops up.
Oh boy, legacy protocol.
Q12 scenario. You discover that several devices on the network are using Telnet instead of SSH for remote management. What is the primary security risk associated with this configuration? Options. A, Telnet does not support IPv6. B, Telnet is not compatible with modern operating systems. C, Telnet transmits data, including passwords, in plain text. D, Telnet cannot be used over wireless networks.
Telnet, wow.
Yeah, I know. This is like Security 101, but you'd be surprised how often old scripts or default settings leave Telnet enabled for managing switches, routers, even servers. Big red flag.
Huge red flag. The core issue here is the fundamental difference between sending information over an open, unsecured channel versus a secure, encrypted tunnel.
And that difference leads directly to the primary and, frankly, catastrophic security risk, which is C, Telnet transmits data, including passwords, in plain text.
That's the killer. If you're logged into a device using Telnet to manage it, every single thing you type, every command, every configuration change, and most critically, your username and password when you first log in is sent across the network exactly as you typed it. Plain, readable text.
Wow.
So if an attacker is simply listening on the network segment, which is easy to do with tools like Wireshark, they can just capture those packets and read your administrative credentials right out of the data stream, instantly.
Game over.
Pretty much. Once they have admin access to one device, they can often pivot from there. SSH, Secure Shell, was developed specifically to fix this massive vulnerability. SSH encrypts the entire management session, from logging credentials to commands to output. It makes that kind of passive eavesdropping completely useless.
It's truly astonishing that in this day and age, devices might still default to Telnet, or even offer it as an option. It's a risk that no network administrator should ever accept. Period.
Absolutely agree. Think about the potential damage. An attacker sniffs one admin password sent via Telnet, and suddenly they might have the keys to your entire kingdom, your core infrastructure. Always, always ensure your management traffic is encrypted using SSH or HTTPS. It's a non-negotiable part of defense in depth.
Okay, let's transition now into Section 4, Network Operations. This is more about the day-to-day and year-to-year administrative side. We're talking planning, documentation, disaster recovery, configuration management, all the stuff needed to keep the network humming reliably.
The operational discipline, very important.
First up, Q13 is about planning for the future. Q13, scenario. An organization is planning to upgrade its network infrastructure. Which type of documentation should be reviewed to ensure the new design will meet current and future performance requirements? Options: A, system audit logs. B, capacity planning reports. C, incident management records. D, user training manuals.
Okay, planning and upgrade, keyword.
Yeah, we're looking ahead. We're designing something new, maybe a faster core switch, a bigger internet pipe, and we need to make sure it won't be overloaded 6 months after we install it. What documentation gives us that forward-looking analysis?
Right. You need documentation that focuses not just on what happened in the past, like incident records or audit logs showing logins, but on what is currently being used and, crucially, how fast that usage is growing and what future demands are expected.
Okay, so that forward-looking, resource-focused documentation, that would be B, capacity planning reports.
Absolutely essential. Capacity planning reports are where you synthesize historical data, things like average and peak bandwidth utilization on key links, CPU and memory load on routers and firewalls, storage consumption.
Right.
And then you analyze the trends. You often correlate those trends with known business projections, like marketing is launching a new video streaming service next quarter, or we're migrating our CRM to the cloud, or the engineering department is hiring 50 new people.
Okay, connects IT usage to business plans.
Exactly. That report allows the network engineers to properly model the upgrade. Will that new 10 gig link really be enough in 18 months based on projected growth?
No.
Will the new firewall handle the increased session count? Ignoring capacity planning is how you end up doing expensive emergency upgrades down the line because you undersize the initial project.
Plan for tomorrow, not just fix today. Got it. Q14 looks at a really important concept in disaster recovery and business continuity.
RTO and RPO always come up.
Q14, scenario. A network technician is tasked with optimizing the network's backup and recovery processes. Which strategy will most effectively improve the recovery time objective? RTO. Options: A, implementing incremental backups instead of full backups. B, using cloud-based backup solutions. C, deploying redundant systems and failover mechanisms. D, scheduling backups during off-peak hours.
Okay, RTO, recovery time objective.
Exactly. The metric is time. How fast can we get critical services back online after a failure? We need the strategy here that most directly minimizes the clock ticking from the moment of failure until service is restored.
Right. And this is a classic question designed to make sure you understand the difference between RTO, which is about time, and RPO, recovery point objective, which is about data loss. Here, we're focused solely on reducing the duration of the outage.
Okay, with that focus on minimizing outage time, the strategy that has the most direct and dramatic impact is C, deploying redundant systems and failover mechanisms.
That's the one. Redundancy, whether we're talking about dual power supplies in a server, redundant network paths, clustered servers, or those FHRPs like HSRP or GLBP we discussed earlier. The entire purpose of redundancy is to minimize the time between a component failure and service resumption, ideally making it near instantaneous or just a few seconds. A primary system fails, and the standby system automatically takes over the workload.
So it bypasses the whole restoration process.
Exactly. It dramatically shrinks the RTO.
Okay, I often see people get RTO and RPO mixed up. Can you quickly explain why options A, B, and D, which are related to the backup process, don't necessarily improve RTO as much as redundancy does?
Sure. RPO, the recovery point objective, is all about minimizing data loss. It asks, how much data measured in time can we afford to lose? Strategies like doing more frequent backups or using incremental or differential backups, option A, instead of just weekly fulls, directly improve your RPO because you lose less data if you have to restore.
Okay, RPO is about the data.
RPO is about the data point you recover to. RTO is about the time it takes to get there. Now, using cloud backups, B, might speed up accessing the backup data compared to finding and mounting physical tapes, but you still have the potentially lengthy process of actually restoring the system from that backup provisioning hardware, installing the OS, restoring the data, testing the services. That restoration itself takes time. Scheduling backups off-peak D affects when backups run, not how fast you recover. Redundancy aims to make the recovery time itself negligible.
That's a very clear distinction. RTO, time, RPO, data point. Okay, Q15 is pure nuts and bolts configuration management on network gear.
Cisco commands, looks like.
Q15, scenario. A network administrator needs to ensure that a backup of the router configuration is performed before making changes. Which command would be used to back up the configuration on a Cisco router? Options. A, copy running config startup config. B, copy running config TFTP. C, backup running config. D, save configuration.
Okay, backing up the config before making changes. Smart move.
It's essential practice. We need to capture the current live operational configuration, the running config, and crucially, store it somewhere off the device itself for safety before we start typing potentially risky commands.
Right. You absolutely have to understand the difference between saving the configuration locally on the device versus copying it to an external server for true backup and disaster recovery purposes.
Okay, so the command specifically for copying the live config to an external server is B, copy running config TFTP.
That's the standard Cisco iOS command for this. It takes a configuration that's currently active in the router's RAM, the running config, and copies it over the network to a TFTP server, Trivial File Transfer Protocol server, which is just a simple server used for transferring files, often configs or iOS images.
Okay. And why isn't option A, copy running config startup config, considered a true backup in this context?
Because copy running config startup config, or the shorthand write memory, or RIMM, simply saves the current running configuration into the router's NVRAM, the non-volatile memory.
So it survives a reboot.
Yes, it ensures your changes persist after a reboot, which is also essential, but it's still stored on that physical device. If the router itself suffers a catastrophic hardware failure, gets damaged, or catches fire, that startup config backup is gone along with the device. Copying the config off box to a TFTP server or FTP or SCP server ensures you have a clean copy completely independent of the hardware, ready to be loaded onto a replacement router if needed. Options C and D are not valid Cisco iOS commands for this.
Got it. Local save, startup config for persistence, external copy, TFTP, for backup. Key difference. Moving to Q16, let's talk about keeping all this documentation organized.
The challenge of keeping docs up to date.
Q16, scenario. You need to ensure that all network documentation is easily accessible and up to date. What is the best approach to achieve this? Options. A, store all documentation in a shared network drive. B, use a version-controlled documentation system. C, print hard copies and distribute them to all IT staff. D, email updates to the IT team regularly.
Accessible and up to date. Both are critical.
Yeah, especially because network configurations change constantly. Just having the files accessible isn't enough if you can't trust they're accurate or know which version is the current one. We need traceability too.
Absolutely. In any reasonably complex environment, especially one managed by a team, if you can't reliably track who changed what document when and why, your documentation very quickly becomes useless, or worse, actively misleading and dangerous if someone makes a decision based on outdated info.
Right. So the best approach listed here for maintaining accuracy, accessibility, and traceability in a dynamic environment is B. Use a version-controlled documentation system.
Definitely. A simple shared network drive, option A, inevitably leads to what I call file sprawl and version chaos. You end up with files named network diagram final to approved usitison.vsdx.
Been there.
We've all been there. You have no idea which one is actually the current correct version. Version control systems, whether it's something powerful like Git adapted for documentation or dedicated document management software with check-in, check-out, and history features, they solve this problem.
How so?
They create a single authoritative source of truth for each document. They meticulously track every single revision made. They usually show you who made the change and when. They can manage conflicts if multiple people try to edit the same document simultaneously. And crucially, they allow you to easily compare different versions or even roll back to a previous known good state if a recent change caused problems.
That sounds essential for things like configuration files or network diagrams.
It is, especially for auditing purposes, for troubleshooting configuration rollouts that went wrong, or just for ensuring everyone on the team is working from the same accurate playbook. Hard copies, C, are instantly out of date. Emailing updates, D, gets lost in inboxes and doesn't provide a central repository or history. Version control is the way.
Okay, we are into the final stretch now. The last domain. Section 5, Network Troubleshooting and Tools. This is where the theory meets reality. Diagnosing faults, using the right utilities, applying that logical troubleshooting methodology.
Where the rubber meets the road, as they say.
First up, Q17, starting right at the bottom layer. Q17. Scenario. A user reports intermittent connectivity issues. The network administrator suspects a faulty cable. Which tool should be used to verify the integrity of the cable? Options. A. TDR, time domain reflectometer. B. OTDR, optical time domain reflectometer. C. Multimeter. D. Cable tester.
Intermittent connectivity. Could be many things, but checking layer 1 first is always smart. Suspecting the cable.
Right. The physical medium itself might be damaged or improperly wired. Which tool is the most appropriate first step for just checking the basic integrity of a standard copper Ethernet cable?
Yeah, you've got a few tools listed there, all potentially useful in different scenarios, but we're looking for the common, purpose-built device designed for that routine check of a twisted pair cable.
Okay, so the most appropriate general tool for that initial check is D-cable tester.
Right. A basic cable tester, sometimes called a continuity tester or wire map tester, is specifically designed for this job. You plug one end of the cable into the main unit, the other end into a remote terminator, and it sends signals down each of the 8 wires, or 4 pairs.
Okay.
It checks for basic continuity. Is the wire broken? It verifies the pinout. Is it wired correctly as straight through or crossover? And it detects common physical faults like open circuits, a break, short circuits, wires touching, or maybe crossed or split pairs. Gives you a quick pass-fail on the basic physical health of that cable run.
Gotcha. But wait, why isn't the TDR option A a better answer? If the cable is faulty, wouldn't I want to know exactly where along the cable the break or short is located?
That's an excellent question, and it really highlights the difference between general troubleshooting and more specialized fault location. A TDR, time domain reflectometer, is a much more sophisticated and usually more expensive tool.
Okay.
It works by sending a high-frequency electrical pulse down the copper cable and then precisely measuring the time it takes for reflections of that pulse to bounce back from any impedance changes, like a break, a short, a sharp bend, or even the end of the cable.
Ah, it measures distance.
Exactly. Based on the timing of those reflections, the TDR can calculate and tell you the distance, often quite accurately, to the location of the fault. Incredibly useful for finding a break in a long cable run that's hidden inside a wall or ceiling conduit. But for the initial, is this patch cable okay? Or is this wall jack wired correctly? Check. The standard, much simpler and more common cable tester, D, is the appropriate first-line diagnostic tool. TDR is more like a step 2 tool if the basic tester fails or if you need precise fault location. OTDR-B is the fiber optic equivalent of a TDR. A multimeter C can check continuity, but isn't designed for checking Ethernet pinouts easily.
Perfect clarification. Step 1, basic cable tester. Step 2, TDR, OTDR if needed. Okay, Q18 moves to network scanning utilities.
Finding out what's running out there.
Q18, Scenario. A network administrator needs to determine if a specific port is open on a remote server. Which tool should they use? Options: A. Netstat, B. Nmap, C. Tracer, D. Ping.
Okay, checking a remote server, and specifically checking if a port is open, meaning a service is likely listening on that port.
Right. We need to actively probe a server that we probably don't have direct login access to and see what services it's offering to the network. Like, is port 80 open for web traffic, or is port 22 open for SSH?
Yeah, so we need a utility that's designed to perform exactly that function.
Yeah.
Execute a port scan against an external IP address.
The definitive tool for that job among these options is Nmap.
Yeah, Nmap, which stands for Network Mapper, is an incredibly powerful and versatile open-source utility. Its primary purpose is discovering hosts and services on a network, and the way it discovers services is by performing port scanning.
How does it do that?
It actively sends specially crafted packets to various TCP and UDP ports on the target remote system. Based on the responses it gets back, or the lack of responses, Nmap can determine if a port is open, meaning the service is likely listening, closed, meaning the OS responded but no service is listening, or filtered, meaning something, probably a firewall, is blocking the probes.
Okay, and again, just to contrast, why not Netstat?
Because Netstat, as we mentioned earlier, shows you the status of network connections and listening ports on the local machine where you run the command. It tells you what your computer is doing, not what a remote server is doing. Ping-D just checks basic IP reachability using ICMP echo requests. It tells you if the host is alive, but nothing about its open ports. Tracer-C shows the routing path. Only Nmap actively scans remote ports.
Nmap for remote scanning, Netstat for local status. Got it. Moving to Q19, let's isolate a very common application layer problem.
The classic I can't get to this one website issue.
Q19, scenario. A user reports that they cannot access a specific website, but other websites are accessible. You suspect a DNS issue. Which command would help you verify the DNS resolution for the problematic website? Options: A. ibconfig-all, B. traceal, C. nslookup, D. netstat.
Okay, the symptoms point strongly towards name resolution. They can get to other sites, so general connectivity is likely okay. The problem seems tied to this specific domain name.
Exactly. So we suspect the failure is happening right at that first step, translating the website's friendly domain name into its numerical IP address. We need a tool to directly query the DNS server and ask it about that one specific name.
Right. You need a command line utility that performs exactly that function, querying a designated name server for a specific resource record, usually the A record for an IPv4 address or a AAA for IPv6.
The correct command for that specific task is cnslookup.
Nslookup is the classic built-in Windows command for this. On Linux and macOS, dig is often preferred as it's more powerful, but nslookup is usually available there too and is what CompTIA typically tests on.
Okay, so how does running nslookup help?
You simply run nslookup followed by the domain name of the website the user can't reach, like nslookup www.problem-website.com. The command will then query the DNS server configured on your machine.
And what results tell you it's a DNS problem?
If nslookup comes back quickly with the correct IP address for that website, then DNS resolution is likely working fine, and the problem lies elsewhere. Maybe the website server is down, or there's a firewall blocking access specifically to that IP. But if nslookup returns an error message like non-existent domain or server failed, or if it just hangs and times out trying to contact the DNS server, then you've successfully isolated the problem to the name resolution process itself.
Perfect. ibconfig, all A shows your own IP and DNS server settings. Tracer B shows the path. Netstat D shows local connections. Only nslookup directly tests the DNS query.
Correct.
And finally, Q20. This is like the capstone troubleshooting logic puzzle, putting it all together.
It's a deduction challenge.
Q20 scenario. You are troubleshooting a network issue where users are unable to access a web server using its domain name, but they can access it via its IP address. What is the most likely cause of this issue? Options. A, the DNS server is down. B, the DHCP server is misconfigured. C, there's a routing issue. D, the web server is offline.
This is a beautiful troubleshooting scenario. It gives you one critical piece of positive information.
Exactly. The success case. Users can access the server if they type in its raw IP address. That single fact is incredibly powerful because it eliminates most of the other potential problems right off the bat.
This is probably the most critical piece of troubleshooting logic you need for the network plus exam and for real-world work. That successful connection via IP address confirms several things simultaneously.
Like what?
1, it proves the web server itself, option D, is online and responding. 2, it proves there isn't a major routing issue, Option C, preventing packets from getting between the user and the server. 3, it proves that the user's own basic network configuration, like their IP address, subnet mask, and default gateway, likely obtained from DHCP option B, is correct enough to reach the server's network. The entire path, from Layer 1 physical connectivity up through Layer 3 routing and Layer 4 transport, TCP connection to the web server port, is working perfectly fine when using the IP address.
Wow, okay. So if the connection works fine with the IP, but fails only when using the domain name,
Mm-hmm.
the problem has to be isolated to the one step that's different between those two methods.
Precisely. The only difference is the initial step of translating the domain name into that working IP address.
Which means the most likely cause is A, the DNS server is down, or unreachable, or misconfigured, or failing to resolve that specific name.
Exactly. The failure occurs only at the name resolution stage.
Yeah.
DHCP is working fine, otherwise the user wouldn't have an IP gateway to even try connecting. Routing is working fine, the web server is online. By elimination, based on the evidence provided, the issue points directly and almost unequivocally to a problem with DNS. That's the kind of logical deduction the exam tests heavily.
Yeah.
#OpperTAC
Wow. Okay, that was an intensive deep dive. If you followed along, you just tackled 20 pretty complex certification level questions. We covered the whole gamut of the Network Plus curriculum.
We really did.
Everything from the physics of single-mode fiber and calculating 28 subnets to understanding why GLBP offers true load balancing, unlike HSRP VRRP, and the absolute critical importance of using SSH instead of plain text telnet.
Yeah.
That level of comprehensive, detailed practice, really understanding the why, is what takes you from just knowing facts to being truly ready for the exam's scenario-based questions.
Absolutely. And we spent a good amount of time really detailing why the answers were correct, like explaining things like 802.1q tagging for multi-SSID setups, or the crucial difference between RTO and RPO.
Yeah, that was key.
Remember, knowledge is, well, it's most valuable when you genuinely understand the technical implications and you can apply the concepts.
Yeah.
For certification prep, that kind of continuous focused practice, especially practice that targets your own individual weak areas, is really the only way to build maximum confidence before you walk into that testing center.
And that brings us neatly to study strategies themselves. You know, the classic challenge for so many Network Plus candidates is just feeling overwhelmed by the sheer amount of information.
It's a lot, yeah.
And maybe studying inefficiently, spending hours reviewing concepts you've already mastered while maybe neglecting the areas where you're actually weak. You really need an adaptive strategy.
That's exactly right. And that's why intelligent adaptive study tools are becoming so vital these days. For instance, you look at platforms like Flash Genius. They're built around an AI-guided learning path.
Okay, AI-guided. How does that work?
Well, it means the system learns your strengths and weaknesses as you practice, so your preparation becomes personalized. It saves you potentially immense amounts of time by focusing your study sessions on the specific domains, objectives, or even question types where you are struggling the most, rather than just making you cycle through hundreds of cards you already know cold.
That sounds much smarter. And I saw they go deeper than just right-wrong answers, too.
Yeah, the AI-powered Smart Review feature is pretty impressive. It doesn't just tell you the correct answer. It provides targeted mistake analysis. It explains why your specific wrong answer was incorrect, details the technical concept you might have missed, and, helps you avoid the common traps and pitfalls that they've seen thousands of other learners fall into.
That constant feedback loop must accelerate learning quite a bit.
Dramatically. And it allows for different modes of practice, too. Maybe one day you really need to hammer down subnetting calculations. So you use the domain-specific practice mode just for that objective.
Right.
Then, as you get closer to the exam, you switch to mixed practice mode, which pulls questions from all domains randomly to really simulate the experience of the actual test and gauge your overall readiness. They even try to make it more engaging with interactive flashcards, gamified elements like a cyberwordle, and even productivity tools like a built-in Pomodoro timer to help you maintain focus during study bursts.
Nice. It sounds like that critical thinking, which is really the hallmark of any good IT professional, is supported by using a modern study tool, something that doesn't just test you, but gives you expert explanations, tracks your weak spots, like Flash Genius. That seems like the best path to really maximizing your confidence and making sure you walk into that exam truly prepared.
Couldn't agree more. Until next time, everyone, keep identifying those knowledge gaps and actively reinforcing your expertise. Don't just memorize, understand.
So here's a final provocative thought for you to chew on as you continue your studies. If you had to teach just one concept from our deep dive today to a colleague right now, Would it be explaining the subtle but crucial difference between single-mode and multi-mode fiber, really digging into the physics of modal dispersion?
Tricky one to explain well.
Or would it be explaining the Gateway Load Balancing Protocol, GLBP, and specifically how it achieves that active load sharing using multiple virtual MSE addresses, unlike HSRP or VRRP? Which of those two concepts would truly challenge you to articulate the why and the how clearly and accurately? Whichever one feels harder, maybe go revisit that topic one more time. We'll see you on the